Hello, this is Ertan Taskin from Ozone Engineering, and in this video, I'll be demonstrating a 2D benchmark case application of a probabilistic inference for Bayesian optimization. So let's start with the workbench project. So in the screen, as you see, we have the geometry with the discovery already put here, and I'm going to demonstrate you the settings and how to make the parameterization. So here is the geometry. As you can see, this is a two-dimensional geometry and a fairly simple structure. I have the inlet region as described here, and the outlet region as described here. And I divided the entire volume into two sections, and I named this portion as the outflow region. So I have 6 openings in this geometry. You can consider this as a very simple, simplified shower head, and we're gonna let the water come from the inlet and then leave from the outlet. And we'd like to achieve a certain uniformity and then a pressure gradient. That's going to be the target of this optimization. You can also notice that this geometry is not perfectly symmetric, and that's going to allow us to see the impact of the diameters of these circles, because they are the parameters, and the parameters are pretty much shown here. And as you see, sorry, as you see here, I have the diameters of all these 6 circles described as the parameters. And if you wonder how to make this, let's assume we'd like to make a change on the inlet diameter or the length. So what we're going to do is select that feature and get to here, and then you will see this add a geometric parameter option here. And once you click that, it's gonna actually make you that length as an additional parameter here, such as when we select it here, the length in this case is shown as the parameter. So when I click this green button, it's going to complete and it's going to appear in this list. But in this model, my parameters are only the diameters of these 6 circular openings. And that's pretty much it in terms of the geometry side. And we will bring the Fluent module and then continue with that. So for that purpose, we're going to go to the toolbox and go to the Fluent, right, and attach to this geometry. And as you see, the geometry is already carried to the Fluent model. We're going to do the meshing and set up solution and results apparently. The parametric setting is already attached to this module as well. So I will skip the mesh settings for the sake of this presentation, but I will go to the setup details. So the Fluent job is already loaded. You can also see it's a very coarse mesh for the demonstration purposes here. And as I explained before, the inlets and outlets are pretty much defined in these locations. So I'd like to demonstrate how to create additional input and output parameters for the optimization. For that purpose, we will get to the name selections region and create a new name selection. So apparently I have already done this, but it's right click and create new. So let's review what I did for the inlet velocity. So if I take a look at that, you will see that this is actually a uniform velocity for this particular application. It's 1 meter per second, and use as input parameter option is selected here. So you have to do this in order to make this as an input parameter. And after you do that, this image here returns to a parameter with a p letter, and also with the arrows going from left to the top of the p to demonstrate that this is actually an input parameter. Similarly, I said I'd like to achieve a certain pressure generation, or a differential in between inlet and outlet region, and this is how I describe that. And also this is now set as an output parameter, and as you can definitely see now, the arrow is actually pointing from the right side of the P. I also wanted to maintain a uniform pressure region, and that's actually the outflow region, which is this portion. As I mentioned before in the geometry section, this is actually an additional a portion of the geometry specified as with a separate name as outflow region. So I wanted to create a pretty uniform pressure distribution in that region. That's why I define my uniformity with that. This is just like a specific application. Of course, you can think of any other parameters that may make sense, or expressions that may make sense for your application. This is also an output parameter. And the rest is pretty much very typical fluent settings with the models and the fluids, and fluid is water in this application. And I didn't get to do any report definitions in this case, but you're free to do, of course, anything. And I will be performing steady state simulations too. So the best practice would be to perform this simulation for the initial settings of the inlet velocity and the initial settings of the dimensional features here. And of course, the outlet pressure was set to the zero pressure here in this case. Once you do that, then you have actually a solution available for your initial design point, as it is named so. And this screen demonstrates you that we have these input parameters, right? The dimensions of these 6 circles, as well as the inlet velocity with these values. And with these values, the corresponding pressure drop and the uniformity values are actually shown here. So after this, what we have to do, we're going to go to the optimization module and bring it to the workbench and make the corresponding settings. For that, what we have to do, again, go to the toolbox, scroll down. We have an optiSLang add-in here. If you don't have it in your workbench, you have to put it from this ACT start page and add in the optiSLang. And what we're going to do, we're going to collect the optimization and drag as a standalone system. So that opens a new screen as an optimization wizard to us, and you will see the input parameters shown here also for this particular application, and the range. So you are free to make a modification. This is just like a default range that the wizard selected for us, but we're not limited to use this. So we can come here and make this a different value, for example. You can make different ranges too. You don't have to make the same ranges for all the features. But in this application, I pretty much did that, and for etc. And for the flow, you can definitely make the range different than what is recommended. We have an also option here. If you look at the constant selection here, you have an option to use one of these or any of these as a constant value. So pretty much excluding the optimization study. So in this particular application, I selected a constant value for the flow, because I know flow is actually could be a primary factor to change the pressures, etc. But I basically wanted to see the impact of the dimensional features, particularly diameters of the circles in this application. So after that, of course, after setting all of these with the corresponding ranges, we're going to click to the next. And the next screen, we have the responses or the outputs are already shown here. So what we have to do, we have to create a criteria for the optimization. We have options of different selections here. It can be an objective, a constraint, and a limit, etc. For this application, well, I will use this pressure drop as a maximum. I want to maximize this. You can consider, whatever makes sense for your application. And for the uniformity, I want to make this a minimum. So here are my objectives. My objectives are already defined here. And as you see, the objectives are selected with the corresponding images here. This is where the arrow going up to indicate the maximum, arrow going down to indicate the minimum of this particular parameter. And in that, we're going to go to the next screen. So the next screen is actually asking us to what optimization method to use. So the default is actually one-click optimization. This is the most computationally expensive option, if you will, and therefore the number of design evaluations, the number of iterations are shown as a default value by 400. So that means the 400 different cases of all these parameters are going to be evaluated to get the best or the most optimum design, right? Based on our criteria. But for this application, I would like to demonstrate you a probabilistic inference for Bayesian optimization, or PIBO option. And that's why you have to go to manual optimization selection and go to and click this one. And with that, it actually finishes. There are other settings that definitely could be explored, but for this particular case, all good right now. Once we click the finish, we're going to have to wait for a while to see how the optimization screen or module is going to be connected to the rest of the system. And as you see, it is already connected. Now, the optimization module is actually attached to the parameter set with the rest of the features. So one further thing that we should do, we have to get here and double click, and now we have this settings option here. This PIBO optimization method starts with these default settings. Now, if you look at these numbers, that means we're going to explore by the default numbers 10 plus 90 iterations. So by default, we are going to do 100 iterations. And if you look, the default option of the previous optimization, which was 400, you can definitely say that there's a 4-to-1 ratio to get the faster results. And also you can select the run mode here. You can select the maximum accuracy or minimum computational time. It's totally up to you. So in this case, I kept it as the maximum accuracy. And for the sake of this demonstration, I just used 10 additional iterations. So I'm going to have 20 iterations to be considered. And with that, we're going to click OK here. and that's it. So what I would recommend to do, and if we get to take a look at this screen is still same, nothing changed here. What I would recommend is to come here and do the update option. And let's open the parameters screen again. We will see how it updates. So as you see, the design point 1, which is actually exactly the same as the design point 0, is completed, and the design point 2 now started. And these are the by default settings of the other dimensions with the optimizer. So we're going to continue until it reaches to totally 20 iterations. So when the total number of design points reach to 10, and if you remember, that was the initial number of iterations that was set by the optimizer, a new window pops up to demonstrate the current status of the optimization with the designs already studied, and among them the best looking ones with the Pareto front profile here. I move this a bit up, we can see it better. And as you see so far, these among these designs, the design 7 seems to be the best one in terms of the considering the objectives of the pressure drop, higher the pressure drop, and the lower the uniformity. And if you look at this screen, these are the corresponding values for the parameters. The diameter 1 is 2.14, the other one is 2.42, 317, 282, 33, etc. These plots in the response data section is actually showing the corresponding size of the pressure drop. That means we are very close to the maximum of the pressure drop with this option. If we select this option, this is going to go all the way to 100. So what we want to do is actually higher the pressure drop, of course, and lower the uniformity, right? And that's pretty much what you can get with this. And similarly, this is the range relative to the criteria that we have set. If we select others, you're going to definitely see that the impact of that. And now, currently, we don't have too many numbers on the far right side of the objective Pareto plot, because there might be, different designs that might be coming out of it later on. But selecting here there, for example, this design, in this case, if you look, the objective wise, it's actually relative to the criteria size, it's pretty much almost full of it, but the because that's the highest one compared to the others, etc. So what we're gonna do, we're gonna have to wait, and you can of course always update this plot. See, there's another data showed right now. That's the design point 5, where all the numbers are in the maximum levels, whereas there, I mean, by just looking at this plot, of course, the criteria range, whereas the response-wise, it's not the optimum, even though by just looking at the others, of course. So let's wait until the total number of design iterations complete to DP20. So when the 20 iterations completed, you will get the screen updated as like this. And this is the new Pareto front plot, where it shows you a good candidates of the selections. And as you see from here, the design selections are shown here with the numbers. Of course, you can go through all these settings one by one, and you can take a look at uh, how um, how the current settings are for these designs. And for this application, design 19 seems to be, I guess, better, but one can go with the design 8 too. They are pretty close to each other, etc. So as you see, this is actually a pretty good tool to to perform an optimization analysis, and some of the features are already presented in this. Also, by just clicking the screen here, we can see the result designs when we look at this tab, and all these 20 iterations with the status of their succession, etc., and the corresponding dimensions, parametric results, as well as the criteria results. So I think this is all for this application, and I hope this would help for the future applications of the complicated systems that you might be working on. And thank you for watching this video.